Thank you, Dane. As Dane mentioned, I'm Ryn Sleesman, CEO of Columbia Power Technologies, and here to tell you about the StingRAY, which you've all learned about on that video. First, though, I'd like to thank the Ocean Exchange team, the sponsors, the delegates for your time, effort, and resources to make this week work. It's actually been a great experience for me. I've really enjoyed actually doing this. So why are we here? One of the reasons that we're here is because we all share this very fundamental need for access to reliable and affordable energy. Now, we don't think about that very much, except when the lights went off at lunch today. Everybody was but it's a very fundamental need. It's a basic building block of any modern economy. So much so that, and you've seen this today a little bit, the UN Sustainable Development Goals. Well, one of those goals is all about affordable and clean energy. Now, this recognizes the transition that we're in to clean energy, but I really wish this actually said affordable, reliable, clean energy. Because as we go through this transition, we're moving from, we all know this, but we're moving from carbon to clean energy. We're moving from centralized to distributed resources. But the biggest thing is we're moving from baseload, stuff that's always on, to intermittent, stuff that's not always on. Now, this transition, I think, we've made tremendous progress, right? This graph shows last 5 years, global capacity net installations. And that's an unmistakable trend there, and that's a great thing. The problem, though, is this is not a sustainable path to sustainability. We can't keep replacing stuff that runs at 90, 95% of the year with resources that runs 20, 25, 30% of the year. It's a solvable problem, though, and one of the ways that we're going to solve this is with batteries. So these big utility scale batteries will actually make wind and solar better. It helps shift energy from times of oversupply to times of undersupply. So helping the reliability, but maybe not helping the affordability. Now, the battery that we like the best is this really big battery. The world's oceans are really just a battery of stored wind and solar energy. And because it's a battery, it can deliver very consistent, reliable, predictable energy. And there is a very material impact that ocean energy can have on the world. The US DOE estimates that 15% of US supply could come from ocean energy. We can supply for countries like Ireland nearly 75%. The International Energy Agency estimates that $800 billion worth of ocean energy capacity will be installed by 2050. The problem, though, is the ocean is a really tough place to operate. It's very germane that WWL is one of the sponsors. They understand that better than anybody. And I, in my very simplistic way, boil this problem of operating in the ocean down to what I call the trilemma. And this is really actually just a sort of a second level explanation of that affordable, reliable, clean energy goal. So to be successful, and these are customer requirements, right? And you can't cheat on one in order to satisfy the other two. But you got to be always on for 20 years. And you can't stop making electricity just because it's stormy or you get big waves. You know we have to be cost competitive at the end of the day. But you also have to be acceptable. And by acceptable, I mean it has to be socially acceptable. So no pitchforks and bonfires from the local community. It's got to be technically acceptable. We have to make grid compliant power. Customers got to want to buy the gear that we want to sell. And it has to be environmentally acceptable. And doing all three of those things at the same time is really hard, and this is why we really haven't delivered on the promise of wave energy yet. It's because nobody's been able to solve this problem. But we believe that we've solved it with StingRAY. So the StingRAY floats on the water surface. It's a megawatt scale unit. It's got composite structure. It's a very simple mooring system, as you see. And these units will be arrayed in farms. So think like a wind farm, but it has a very low profile on the ocean. You really can't see it from the shore. And we like being in deeper water, more than 50 meters. And these units, these wave farms, will produce utility scale electricity. They're grid connected. And we know this works because we've been at this for quite a while. So the technology started at Oregon State University, was worked on for 5 years. We've been working on it for 10 years. We've tested it for 12,000 hours, done extreme survivability testing. We were in a sea trial for over a year. We've been certified by DNVGL, which is the largest independent certification association in the world. We've got 14 patents. We've won 14 federal grants from the US Department of Energy, Navy, and DARPA. DARPA is the Advanced Research Group for the Department of Defense. So as Millie mentioned yesterday, I won't get into the weeds, which is good because I'm not an engineer, which, as I like to say, means I'm not encumbered by the facts. It's a very simple operating system. So it's 2 floats, fore and aft, and the waves are coming from your right to left. Each of those floats drives its own generator inside that central cylinder. So that cylinder we call the nacelle. So 2 floats, 2 generators, 1 nacelle. And we can talk about this some more in the Q&A if you'd like to. So some of our advantages, and this is an important one. We use essentially the same type of generator that you see in a wind turbine. And that's important for a number of reasons. 1, it's a well understood technology. 2, our customers, potential customers, buy billions of dollars of this type of gear every year. So when they look to us, we just don't look that different. Very important. And this technology also scales. This type of generator also scales very well. So what's important if we're going to, again, match the affordable side of that goal, you got to be able to concentrate as much power in that installation as you possibly can. So offshore wind turbines have gone from 2 megawatts per unit to 4 to 6 to 8, now heading to 10. And this technology, this type of generator is unique to us. We're the only ones currently that can use that. We use composite structure to avoid this problem. Steel obviously corrodes. We were the pioneer actually in the industry for using composite structure. And we have a strategic investor that's the largest specialty manufacturer of fiberglass in the US. In every wave, there's actually 2 forces. There's the heave force, which lifts you up if you're at the beach, and there's the surge force, which tries to knock you down. And what's important about that is if you can't potentially capture both of those independent forces, then you're literally leaving 50% of the energy in every wave on the table. We access both heave and surge. And our system, as I said, is very simple. So we use a direct drive permanent magnet generator, which allows us to have a single energy capture conversion cycle. Can't be any simpler than that, can't be any more efficient than that. So what's important about all these advantages, I think, is that no one can match all of these together, much less even 2 of them. So we're going to go to market in Europe. And why Europe? Well, Europe is the early adopter for renewables. Onshore wind, solar, offshore wind, tidal energy is now commercializing in Europe. Wave energy is next. And the Europeans are really quite good at creating the market push and pull mechanisms that are necessary in order to bring a new technology, a new resource to bear. So they have this really incredibly aggressive goal, 4 gigawatts by 2020 for ocean energy, and that's tidal and wave. They won't get there, but even yesterday, the EU announced a $350 million investment fund specifically for ocean energy. It's an incredible commitment. And one, I think, well, the latest example, offshore wind. So 10 years ago, there was basically no offshore wind capacity in Europe. As of the end of last year, there was over 11 gigawatts. Here's what that growth looks like. That's an incredible amount of work. And the end result of that is that Vattenfall, the Swedish utility, last week put in a bid for 6 cents a kilowatt hour for a 600 megawatt offshore wind farm. They turned what was a very expensive resource into a very cost-competitive resource. Our business model as we go to Europe is about equipment sales. We don't want to own the capacity. We don't want to own the projects. We need strategic partners to help us make those sales. We need strategic partners to help back the warranty. You know, a potential customer, utility, independent power producer is going to look at us and wonder who's going to backstop that warranty in 5 years. The nice thing about these units is they get made in a shipyard. So we get to avoid the cost and the time of having to invest in manufacturing facilities. So our competition, we've got to be cost competitive at the end of the day with all of these resources. That mix will change over time. But again, at the end of the day, we have to be cost competitive without subsidies in order to make this work. Our direct competition, and I know you're all amazed that we're at the upper right of this chart, but our direct competition is global. We are what I refer to as the pre-commercial validation phase. We have our go-to-market design, and we are in the final steps of testing that design in the generator. Now, we put the distance between us and our competitors because their competitors have 2 issues that they're either working through. One, they have a major subsystem change, generator mooring, that they've got to go through, and it takes time to grind through this. or they're in earlier R&D phase and still trying to work out some of the fatal flaws. Along the way to solve the trilemma, our innovation has also enabled some other market opportunities for us. So I'm not going to dive deep into this. I'm just going to give you the 50,000-foot view, but it's really important, I think, to what we can accomplish with some of the innovation that we've done. And one other thing about innovation. So for us, there's two tricks that we have to solve. One, we have to create some novel innovation, but we also have to take garden variety, well-understood technologies like the generator or the mooring system and combine those in a package which answers the trilemma. But our innovation has created an opportunity to make large diameter generators bigger, more productive, more efficient. More on that in a little while. But it offers a very significant step change reduction in the potential cost of energy. Back to batteries. So batteries are used in order to run sub-kilowatt scale equipment, buoys, sensors, monitoring equipment. There's a fish aquaculture. There's a whole lot of uses here. The problem is batteries are an issue, obviously, in the ocean. Our technology scales very well from the utility scale unit, which is very large, to a very small footprint unit, which can produce hundreds of watts in order to keep those batteries topped off indefinitely. So we're going to lower the cost of ownership. We're going to increase emission persistence and also allow bigger payloads. We got a great team, love working with these guys, some of the smartest, hardest working, most capital efficient people that have ever been around. Between our team and our board and advisors, we've got significant experience both in early stage and Fortune 50 companies. We've started companies, we've sold them, we've taken them public, developed over $1 billion of wind and solar facilities. We've got the core group that we need to execute on our plan. We have some spots to fill, but we've got the core group we need. We've also created a great supply chain to help us go to market. And our federal partners have been critical to our success, DOE, Navy, and DARPA, and also the Oregon Wave Energy Trust. We wouldn't be where we are today without them. So I've got kind of a busy milestone slide I'm going to show you here in just a second. So a couple notes. Those of you that aren't familiar with the technology readiness level scale, it's a technical maturity scale that NASA, Department of Defense, DOE use in order to gauge where you are relative to commercialization. So TRL 1 is an idea. TRL 9 is a product that you can buy off the shelf. So it's a busy slide because we've been busy, but just a couple takeaways here. One, we've had very rapid, steady milestone achievement. We've had a number of technical breakthroughs that have enabled that milestone achievement. And through that jumble of numbers at the bottom, I think the great takeaway is we've been incredibly capital efficient. We've gotten as far as we have with 1/4 to 1/5 of the capital that some of our competitors have required. So if we are fortunate enough to win, what are we going to do with the proceeds? This is a project that we have that's just starting. It's co-sponsored by the Department of Energy. And what you see here is on the right, that large blue piece of equipment is a dynamometer. It's a test motor. Usually you see a wind turbine nacelle hooked to the end of that doing life cycle testing. And this is at the National Wind Technology Center in Boulder, Colorado. It's run by NREL. So in the middle there is our generator. And that rotor is 6.5 meters in diameter. It's a really big piece of gear. And part of the innovation, part of what enables this generator work in our purposes and what may apply back on the wind side, or we believe does apply back on the wind side, is that we can maintain a 4-millimeter air gap around that entire circumference between the rotor, which has the magnets in the generator, and the outer ring that it spins inside of that contains the copper coils. That's a really small distance to maintain over such a large diameter. On the left, you see the test stand. But this is a very critical test for us. It is a huge risk reduction step. We saw tidal energy companies in Europe avoid this full-scale generator test before they went into the ocean. And we're going to go into the ocean. This test here, gets us to TRL 6, and that'll happen in the next few months. We're going to be moving to TRL 7 with a test in the open water at the U.S. Navy's test facility in Hawaii. They just created a deep water berth. It's grid connected. And we'll move to TRL 8 with the first unit that we put in Hawaii, in Europe. So this is a very critical precursor that we have. So with that, I will say thank you very much. Appreciate your time. And look forward to your questions.
Brent, thank you. Great job.
Thank you.
So, questions? One over here.
That was very, very good, thanks. So in terms of where this technology can be deployed,
Yes.
in terms of wave energy intensity and so forth, what restrictions do you have, from a geographic standpoint? And I keep thinking of Jim Gordon and Cape Wind. It took him forever to go through the regulatory side on offshore wind. What, if any, regulatory issues do you have to work through on the on offshore wave energy?
Sure, that's a couple of really good questions there. So where do we want to be, or where can we be? Well, I'll answer it by saying where we want to start. We want to start in the most vigorous resource, so off the coast of Europe, Pacific Northwest. The best resources are where there's a long open fetch of water. We're not dealing with wind-driven or short-term wind-driven waves. These are waves that started a long time ago. So on the Pacific coast, those waves literally start on the other side of the Pacific. Well, that's where we want to start. We really need to be in the temperate zones. As the technology matures, we'll be able to work our way towards equatorial zones. There's really no restriction on where we want to be. We like being in deeper water, which is nicer because you're a little bit out of sight, out of mind. Environmentally, I think that the problems that Cape Wind have are exactly why we want to go to Europe. So in places like Scotland, which wants to be the center of gravity in Europe for wave energy, for ocean energy, they actually have this battle cry, which is we want to be the Denmark of wave energy. Which refers back to Denmark's leadership in wind. But they have created streamlined environmental permitting there. So Marine Energy Scotland is a one-stop shop. You can really get through there in about 6 months. They've already started to lease the seabed. The Crown Estate, which owns the seabed in the UK, has already put out 600 megawatts of leases for ocean energy. So it's a environmentally, though, things that we need to worry about when we get into the nitty-gritty, we got to worry about mammal migration. That's why we have a very simple mooring system. We try to reduce the footprint as much as possible. We actually refer to that as a single-point mooring. Crabbers, fishermen, they're excited about, well, they can't be really excited about having another use in the ocean. It's something that they've been asking for. EMF, electromagnetic, worrying about the signal that comes out of the line. That's something else that people worry about. BOEM, which is the former MMS, actually just did a study. The oil platforms off the California coast are all grid connected. And there happens to be 2 cables almost side by side, one of which is energized, the other of which is dead. And they did a study and they found that there was no difference. So we're starting to believe that EMF, and there are a lot of power cables in the ocean, so EMF, which can be a significant issue, that's starting to go away. So we have to worry about spatial planning, which is not necessarily an environmental concern. So there are other prior uses of the ocean that we need to work around. So there's a lot of things that we need to deal with. But again, it's one of the reasons why you start in Europe, because they tend to take you don't have to do all that in advance, you can do it in parallel, so you can get stuff in the water quicker.
Got one more over here.
Yes.
And you're next.
Cope with the variation of directions, because you have a more or less single point mooring.
Yes.
So is it possible to turn around 360 degrees several times?
No, so we keep station, sorry, going the wrong direction. If I can get back there quickly.
Can we get the graphics to the screen, please?
Okay, so this is a simple representation, but you have this single point mooring in the front, and then you've got a tail line in the back. We basically keep a pie wedge, a triangle. So one of the things, because we're not that far off the coast, where if you look at the wave rows, if you look at the predominant directions that the waves come in, they're usually fairly concentrated in a single direction. We're not going to obviously see waves coming back from the coast. So at most, we're worried about 180 degrees. Those lines are strong enough. Again, we were certified by DNV. Those lines are strong enough to deal if you happen to have the off sort of 90-degree wave. The unit wants to naturally align itself in the wave direction as part of the hydrodynamics of our system. And off-angle waves, so even though you like to think waves are perfect, Every wave is a little different than the one that came before it. It's a little off angle, but the system deals very well with that off angle. We don't lose a lot of conversion efficiency with that.
We're next here.
Hi.
Hi. I was just thinking about what you were talking about the crowded space in the ocean, about how we're learning how crowded the space is actually with marine spatial planning. So I was thinking about the scale. I don't
Yes.
understand the scale of your
Yes,
in the farm.
right.
But then I'm thinking about existing infrastructure. Can you apply the farm in places where we already have wind farms, or do these really have to be separate? Can you piggyback on already existing infrastructure so you're not competing for new space?
Right.
Can you? Yeah.
Okay. So, yes, there are obviously a lot of uses in the ocean. Our system on the Pacific Northwest, I'll use that. So it gets deep fairly fast off the Pacific coast. So about 2 miles out and on is where we can be. So it's roughly 2 to 15 miles. So if you think about the entire coast, that's a pretty big chunk. And yes, there are navigation lanes, there are other prior uses, but it's reasonably wide open space. So that it's an issue. We have to deal with that. Coast Guard's involved in that. There are a lot of different groups that are involved in that. But I think that's workable. I think there's a lot of opportunity there. And I neglected to talk about size. So utility scale StingRAY is roughly 25 meters in each direction. When it's fully ballasted, it's about 1,000 tons. It's a very significant piece of gear. But again, if we're going to make utility scale electricity, it's got to be substantial. We believe that we can fit about 10 per square mile if you think about arranging those pie wedges so that we're never going to bump into each other. That's about the density that we can get to.
Over here.
What is your solution for dealing with biofouling, having a mechanical device on the surface with something that has to stay buoyant?
Yes, so the biofouling is actually a little bit of a mixed blessing. That weight, and I'm glad we're on this picture, so the plate that you see at the
Can we
bottom.
go back to the graphic? Thanks.
Yeah, thank you. The plate that you see at the bottom provides inertial resistance. So the unit works.
You got a laser pointer on there.
Oh, yeah, there we go. So this plate here is meant to keep the nacelle out of phase with the floats. So if you think about a wave being a sine curve, the floats are going to follow the sine curve. We make electricity by exaggerating the relative movement between each float and the nacelle. And so this plate here helps keep the nacelle out of phase with the waves. So it's but the biofouling, I almost forgot the question. The biofouling, that extra weight, that extra resistance is not necessarily a negative, but we still have to deal with it, right? There's still going to be a beard that's going to grow on this thing. And that's usually dealt with August or late summer tends to be maintenance month is going to be maintenance month for farms. So it'll be a diver out there basically, or a set of divers out trying to get rid of some of the growth. But it's not going to necessarily harm the production of the unit, but we can't let it go forever. We have to worry about birds on top. We got to worry about seals hauling out on the unit. So there's some things that we have to do in order to protect the unit. But as far as the biofouling goes, there will be some coating on there, but it's not at the end of the day for us an overly critical or something that we can't conquer. But it's a great question.
We've got a couple, but I have a question. Just a sense of scale of the thing. How big is the actual unit?
So this unit, if it was off the coast of Oregon or Scotland, would be literally 25 meters in every direction.
Okay.
It's big.
Big.
It's big.
Okay. I think you were next over there. And then
I have two questions actually.
Okay.
One is the levelized cost of energy, if you compare it, for example, with offshore wind.
Yes.
That's one question. And,
Yes.
and the second question is, how do you deal with the really rough waves, the 100-year waves, for example?
Yes. Okay. And that's actually great questions. So the levelized cost of energy, the first one that goes in Hawaii is a work of art. One of the reasons that we like composites is that is actually an automated manufacturing. It's a filament winding process that you can literally have somebody leaning against the machine while they watch the unit get wound. So we can mass produce the units and we can get to scale. But that first one, it is roughly 40 cents a kilowatt hour. It's a very expensive piece of gear. Now, the first threshold that we need to get to, offshore wind just a few years ago was roughly 15, 20 cents a kilowatt hour, and that was still a multi-billion-dollar business in Europe. So that's the first threshold that we have to get there, or get to. We'll get there with controls, we'll get there with scale as we make the unit bigger. Again, that central nacelle, we like that big diameter. It makes the unit actually capture more energy, but it also gives us the space in order to make that generator bigger. So when I talked about offshore wind going from 2 to 4 to 6 to 8 to 10 megawatts, it got bigger because you can make the generators and the blades bigger. I can't promise we'll ever get to 10, but that's part of the things that will help us drop the cost of energy, and 20 cents a kilowatt hour is the first stop for us in Europe. And then the second question, I already forgot. Sorry?
100-year waves.
100-year waves. Okay, so I'm going to have to skip all the way to the end here.
Let me see the graphics, please.
Yeah, thank you, Dane, for keeping that. Okay, so a number of the technical breakthroughs that we have. One of the units that we have, which is, it's not caught up. Okay, it's really, there we go. I was going to say it's this really beautiful piece of equipment, but this is a unit that we tested, and those are in-stops. So those prevented the two floats from banging into each other, and what we learned is that was not going to scale. You could not make a utility scale system with the in-stops. So one of our guys had an aha of, well, why don't we just back the aft float up? So in a heavy sea, what's going to happen is that forward float's just going to roll right over the top, and it's going to nest itself inside of that aft float. The unit's still working. There's no cutout. It's still operating. It's not as efficient as it would normally be, but that was a very elegant solution to a very significant problem, because if we lose control of the farm, they're all connected by fiber optics, but if you lose control of the farm, you can't have it beat itself to death in a bad storm. So that's how we deal with the 100-year storm, where we're still making potentially electricity, and we don't have to hide from it, but the unit's not going to beat itself to death. And we have to go through the 50, 100-year storm are engineering or levels that we need to engineer to ensure that the unit will survive. And that's actually part of that certification process, is doing case studies and trying to understand how the unit operates in the 100-year storm.
Jeff, you're next. Last question.
So first, just a clarification.
Sure.
The award, should you receive the award, will be used to help achieve the TRL 6
Yes.
certification.
Yes.
I think I just want to make sure it's clear.
Yes.
And the other is that I think that a lot of us are focused on the units that are out at sea, and what I'm interested in, because I'm behind on my knowledge of this, is
Yes.
the growth in the technology of the transmission cables themselves, so that you actually can get it to the grid. And I appreciate sort of a very short summary of where we're at in that technology.
Yeah, my answers have been a little long. So if you think back to that picture of the unit in the water, really our innovation is like a bubble around the yellow unit. Everything else is pretty well-worn, well-understood technology. The mooring line was designed by an oil and gas platform mooring company. The undersea cabling is really well understood. There are thousands of miles of power cable that are laying in the ocean now. The transformer, the subsea transformer that brings the electricity from each unit to connect to that export cable. Actually, GE has already built one for one of the tidal projects in Europe, actually in France. And Alstom started it, but GE is obviously finishing it. So we are watching the rest of the world sort of take the parts forward, and we're focusing there on the unit itself.
Great. Thanks.
Thank you very much.
Good job.
Thank you.